All right, welcome. Thanks for joining today. I know it has been an exhausting week. We are all tired. That's why I really appreciate it that you still joined here. You might also hear it in my voice. It suffered also from the whole week of speaking. But we get through this together. So, hi, my name is Dirk. I'm a solutions architect with AWS, and I'm from Germany, so you can enjoy my funny accent today. Why are we here in the first place? So, when you talk about software architecture, I think two aspects are very important. One is divide and conquer, the other is loose coupling, and particularly loose coupling and not lousy coupling. And when you deal with microservices, you already apply divide and conquer. And a good way to apply loose coupling is asynchronous messaging. When we talk with customers and discuss about the communications architecture between their microservices, we often hear that they have REST APIs on their radar, but not necessarily asynchronous messaging. And we think that messaging can have a number of advantages in certain architectures to help you evolve and scale and operate your services independently. So when you looked at the session catalog, the title of my talk, who actually thought, why should these patterns only be interesting for microservices? Shouldn't those patterns be relevant for all kinds of architectures? Did anyone think this? Very good, 3.5%. And you're absolutely right. Actually, the session title could also be application integration patterns, not only for microservices. But as I pointed out before, in particular for microservices, it's worth to have a look at asynchronous messaging. Quick look at the agenda. So I will have 1-2 sentences more of introduction, and then I will dig into some fundamental application integration patterns that are mostly built on asynchronous messaging. But to make it more tangible and put more flesh to the bone, I also brought a number of real-world use cases so we can enjoy these. We use a fictional technology startup for that, and I think it's quite entertaining. Related breakouts are probably not relevant anymore. This is all gone. Okay, one more sentence of introduction. I like to start with a quotation from one of my colleagues, Tim Bray, who is Distinguished Engineer for AWS Messaging and Workflow Management. What he says is, if your application is cloud native or large scale or distributed and doesn't include a messaging component, that's probably a bug. I guess he's right. Why is that so? Because synchronous systems come with inherent coupling. And if you think about the request path that you see throughout your microservices landscape, when something goes wrong in there, problems can accumulate and put your entire system at jeopardy. That's why we have mitigation patterns like circuit breaker in the first place. To bring everybody on the same page, I want to discuss now a few fundamental application integration patterns with you, mostly based on messaging. And patterns are really a great means for architects, but not only for architects, to discuss things, because they provide a lingua franca, so everybody knows what the other is talking about. I'm sure you apply patterns in your work life. Maybe you know the Gang of 4 pattern catalog and use that for software design. Who is doing that? Quite a few. Cool. And for application integration patterns, I would consider a certain book also a standard library for application integration patterns. It's called Enterprise Integration Patterns, authored by Gregor Hope and Bobby Wolf. And I want to share some of the fundamental ones with you. And let's start at the very beginning. Message exchange. We can distinguish between one-way and request-response messaging. One-way messaging means we have a sender, we have a receiver, and a message channel in between. And we can immediately see The idea of messaging, the message channel decouples sender and receiver from each other. They don't have to know, and they don't know about each other. So there's no response expected here, and we can further distinguish between synchronous and fire and forget. Why synchronous? We're talking about asynchronous messaging here, yes. But this relates to the communication between the sender and the message channel. So the sender might not even be interested in getting an acknowledgement from the message channel. On the other hand, request response. Here we have also a return channel because the requester expects a response for the initial message it sent out. This might raise two questions with you. How does the responder actually know where to send its response to? For that, we can apply the return address pattern. So the sender injects a piece of meta information into the message, and the responder can extract it and derive from there what the return channel is. Now, also, if an incoming response arrives at the requester, it has to know how to assign it to a previous request. For that, we have the correlation ID pattern. Again, it's a piece of meta information that the requester can inject into the request message. And the responder is asked to forward this correlation ID into the response message. But now let's understand the message channels better. We can distinguish between point-to-point and publish-subscribe channels. Point-to-point channels are implemented by queues. Publish-subscribe channels are implemented by topics. The semantics of a queue are that every message that is sent into a queue is delivered by the queue to one receiver. You can have multiple receivers, and the queue distributes all the messages across the receivers. So that comes with two really great advantages. First is you can really easily scale out on the consumer side. That means if there is a lot of traffic on the queue and the existing consumer processes are not capable anymore of processing all that load, you can simply add more processes, and then the queue will distribute the load also on the additional ones. In that sense, the queue acts as a load balancer. And since messages are usually also buffered in a queue, we can consider it as a buffering load balancer. And that brings us to the second great advantage of a queue. It can flatten peak loads for you. Because it buffers the messages, even if you don't have enough receivers that can immediately process all the messages, you can process them at your own pace, and maybe you don't want to scale out as much as it is necessary to process them immediately. Maybe you can wait a bit, and then you can save money by not running so much compute on the receiver side. Let's have a look at the semantics of topics. Here, every message will be delivered to every subscriber. The receiver side is called subscriber now. That means if you look at the case that we discussed previously, if there is a lot of traffic on the topic and each of your processes is not capable anymore to process all these messages, you cannot simply scale out by adding more subscribers, because any additional subscriber would also receive all messages. So that doesn't help here. We can park this problem for a bit. We will come to a composite pattern soon that solves it. Also, usually topic messages are not persisted, but you can apply the durable subscriber pattern to have that still. Now you might ask yourself, wait, why are topic messages not persisted? I use Kafka and they are persisted there. That's right for Kafka, but Kafka is a streaming product and not a messaging product. When you want to implement something and really make use of messaging, for cloud-native workloads, we have Amazon SQS and Amazon SNS. They are both cloud-native services and serverless services. So that means there's no infrastructure whatsoever to manage for you. You can just consume the services through a simple API. But you might also have the requirement that you need to support industry standard messaging protocols like JMS or AMQP, maybe in a legacy workload scenario, in a lift and shift scenario. Then you can make use of Amazon MQ, which is a managed active MQ broker. There are a few terms in this context that you should understand when you deal with messaging, when you build workloads that deal with messaging. Visibility timeout, in-flight messages, and message acknowledgement. Let's have a look at a visibility timeout. So if you look at Amazon SQS, for instance, we have that blue message A here. If it is delivered to a receiver, then message A becomes invisible for all other consumers during the visibility timeout. What we can see here in this picture, the message is processed on the consumer side and eventually acknowledged. Acknowledged means it will be deleted from the queue, and in the SQS example, there's an explicit delete operation for this. However, the message processing can take longer. Maybe the processing code needs to wait for a database transaction or something. When the visibility timeout is over and the message has not yet been acknowledged, it will become visible again for other consumers. That's something you want to be aware of. While a message is in processing, we also call it is in flight. Now let's have a look at a few composite patterns that make use of the few fundamental ones that we've seen so far. Topic queue chaining is the solution to the problem that we saw before when we wanted to scale out on the subscriber side. We have again a publisher that publishes messages into a topic. Now we don't attach our subscriber directly to the topic, but we put a queue in between. With that, we can have the best of both worlds. So we have fan-out functionality, and at the same time, we have also consumer scalability. Also, since queues persist messages or buffer messages, if there is an outage on one of the receiver applications, the messages will not get lost. Speaking of outage, I know you all test your code really well. Still, sometimes it happens that an exception raises in production, unfortunately. So let's assume the situation, a message is delivered to a receiver, exception, goes back into the queue. Again, delivered to a receiver, exception, and so on. Such a message is also called a poison pill, although it doesn't necessarily have to be something malicious. It can really only be that the receiver assumes certain states are present and they are not present anymore. So you actually don't want to operate on the open heart, but would like to get this message out of production and investigate without the hassle. For that, we have the dead letter queue pattern. You can configure on the queue how often can a failure occur until the message is rerouted into a dead letter queue. And from there, you can investigate what was the reason for it and later put it back into the queue. I'm very happy that also Amazon SNS supports now dead letter queues. So even with failures on topic message consumption, you can then reroute them into a dead letter queue. Sometimes you might get the requirements from somebody, I really have to make sure that message order is preserved. Sometimes the requirement is even valid. For that, we have FIFO queues. First in, first out. If you look at the example, the message order is preserved. Order exclamation mark reminds me of John Bercow. Who knows John Bercow? A few? Not so many people from Europe here? Okay, former Speaker of the British Parliament. Okay, but if you think about it, if you want to preserve order in your messages, it will probably not work in a multi-threaded environment. That's why you have to pay for it with a limited throughput. If you compare the throughput of Amazon SQS, a standard queue, and a FIFO queue, FIFO queues have dramatically less throughput. And that's the same for any other messaging or streaming product when you want FIFO behavior. At some point in time, you have to have a single thread working on something. But it has also another aspect that you should take into account. You cannot have more than one receiver on your side. Because if you have multiple receivers that act concurrently on the incoming messages, you cannot guarantee on your end that you preserve the message order. Because message processing is probably not taking the same amount of time every time. So what can we do to still have at least a bit of scalability options on our receiver side? We can try with a message group pattern. We can now attach an additional property to a message, and each concrete value that this property has can be interpreted as a message group. So with that, we can at least scale out on the number of values that we have for this property. If you look at this example, let's take the colors as message groups. So we have 3 groups, the blue, the yellow, and the whatever that color is called group for message D. Message A is delivered to one receiver, message B to another, message B is consumed. Now, in the order of the messages in the queue, actually message C should be delivered. But the way Amazon SQS, for example, would do it is to park message C as long as another message of the same message group is in flight. So instead, message D is delivered. Eventually, message A is also done. And now it's only a matter of concurrency, which of the subscribers, consumers, will get remaining message C. In this case, the one at the bottom. You might also bump into the term message delivery QoS, quality of service. We can distinguish between at least once, at most once, and exactly once. Sometimes you might get the requirement, I need exactly once delivery. You can imagine that this also comes at a cost. And as a matter of fact, you can hardly really guarantee this in practice because of yourself. Imagine your receiver code runs into an exception, but the message has already been delivered once to this receiver. Maybe this receiver has only processed the message 50% of whatever work needs to be done, and you want to fulfill the full 100% of the work that needs to be done. So you actually want the queue to deliver that message again. And then it is delivered a second time, so no exactly once. However, there's also ways to mitigate this. So messaging systems would usually also enrich the message with meta information that advises the consumer, okay, I have delivered this message also earlier. But as a rule of thumb, if you really want to do messaging at high scale, it can only be at least once delivery. Let's have a look at a few other very helpful patterns. Message filter and recipient list. We said for topic messages, every subscriber is interested in every message. However, it might be the case that you have the situation where certain subscribers are only interested in a subset of your messages. You can do one thing now, create a lot of topics to cover all these exceptional cases. or apply the message filter pattern. So here, every subscriber can autonomously tell the topic, hey, I'm only interested in blue messages, for instance, or the yellow messages. And of course, the publisher remains unaware of this. The publisher doesn't know about the subscribers anyway. This is a great example to also show that it is more effort to have this functionality without messaging, because recipient list would be a pattern to implement this without messaging. Here we have additional code and infrastructure that knows which subscriber is interested in each message. So that means for you, more code to maintain, more infrastructure to maintain. You can have the recipient list as a separate process or add it to the publisher. And it also then couples left and right more together. So the message filter option is definitely the better way to go here. Another pattern that is very interesting, particularly in parallel processing, divide and conquer scenarios or RFQ scenarios, is scatter-gather. Imagine you want to send out an RFQ. So you could send your RFQ document into a topic. Your potential vendors would receive this from the topic. They can work on their individual quote, send their response back into a queue, and from there you can aggregate and process it. We will have a nice use case with our fictional startup in a bit. If you rather want to implement a processing pipeline, a sequential processing pipeline, you can apply the pipes and filter pattern. So you have an event source and a result target, and you can have multiple steps in between where transformation work is done on your initial event. You use a message queue and a piece of code for each step. Since it can become a quite long pipeline, and since all the filter steps here need to know about the next step, you add a bit of a coupling between all these steps. So it might not be the best way to implement something like this. Similar patterns or other names for this are chain of responsibility, or also Saga choreography. Saga is actually a good keyword here. There's another flavor of Saga, which is called Saga orchestration. And that might be a better solution with even more functionality. Again, we have an event source and a result target. Now we have an orchestrator component. With this pattern, we externalize the knowledge of the processing steps into the orchestrator. And the orchestrator can do all the work for you. And additionally, it would also allow for branching, parallel processing, and retry scenarios. If you want to make use of that pattern, it's a great use case for AWS step functions. AWS step functions is a serverless and cloud-native service that implements state machines for you that you can use to apply the Saga pattern. And you can define these state machines in a JSON document or even paint them in the AWS Management Console. Okay, so with these patterns that we have seen now, let's jump into a number of concrete use cases to make it more tangible. The context is our favorite fictional startup called Wild Rides. What does Wild Rides do? Well, it disrupts transportation by replacing traditional taxi cabs with unicorns, because it's much more fun and much more magical to ride a unicorn than to ride a taxi cab. And Wild Rides has a massive microservices architecture, and they have a number of really interesting use cases. The first one is rather trivial, though. Submit a ride completion. Imagine you have been delivered by a unicorn back to your hotel, and the unicorn wants now to submit this information, successful delivery, I eventually want to have money, want to send this information to the Wild Rides backend. So it uses the Wild Rides Unicorn app, and the app communicates with the Wild Rides backend through a REST API. The examples I show here are also really helpful to understand how you can still have synchronous communication through REST APIs between end-user client and an entry point in the backend, while you have asynchronous communications under the hood. So the Unicorn Management Service receives this request, and it would probably first thing store the request payload into a database. It can then respond to the client, 201 created, I have that new resource, it looks like this, all good. Now, as said, there are a number of other microservices in the Wild Rights architecture, and some of them could also be interested in the fact that a customer was delivered and a write completion message was sent. A few examples are listed here. The customer notification service, loyalty service. Of course, there has to be a data lake ingestion service because everybody has a data lake, and also Wild Rights have one. And we have a very special one. It's called the Extraordinary Write Service. And this one is only interested in messages or in writes that have a certain fare or distance beyond a certain threshold. Okay, how could we integrate this? I mean, the Unicorn Management Service has stored the information in a database. It could simply make the database also accessible for all other services. Who would support this approach? Can I see some hands? Maybe half of a hand or so. Please not. No, we don't want to do this. So we would tightly couple all the code in the services on the right-hand side to our database schema. And if I may borrow a joke or a statement from Roy Fielding, he would say, there's so much coupling involved, this should be X-rated. We don't want to do this. Integration via database, no. Integration via REST APIs, maybe. I love REST APIs. They are great. They are based on the web architecture. Who would support this approach? All right. It's an absolutely valid approach, but in this scenario, it might come at a cost. So we have now REST APIs on all those services. So the Unicorn Management Service somehow needs to send HTTP requests to them. But it has to know where to send them. So we would have, again, the recipient list pattern. We could also externalize this into a request distribution service. Additional code, additional infrastructure. We would also have to implement ourselves the filter for the Extraordinary Write Service. Something that we not really want to do, because we would rather focus on our business model and improve our software for our customers and not work on additional infrastructure. What about integration via messaging? Who would support this? Okay. And who only raised their hand because it says absolutely? Awesome. That's fine. That's fine. Yeah, it's really easy to use messaging here. We could simply put an SNS topic, the write completion topic, let all the services subscribe to that topic, and the Unicorn Management Service can send out the information into that topic. And also we can simply make use of the SNS message filter functionality. The Extraordinary Write Service can simply send a filter policy to the topic, and then we're good to go. Now, if we also want to become resilient for outages on the server side, on the side of the other microservices, we can put queues in between, apply the topic queue chaining pattern. And then that also supports scalability, as we have seen before. Okay, so that would be a good architecture for this use case. Let's have a look at the next one. Pre-booking campaigns. So Wild Rights runs marketing campaigns and has the CTA, please book your campaign for next week already this week. So Now we look at the Wild Rides customer app. There's an API resource, submit ride pre-booking, and it is exposed by the ride booking service. Again, it would probably store it in the database, but of course it would not share the database with other services, and can respond to the client, hey, hi, I've created your pre-booking resource for you. You're good to go. Now they run a massive campaign with the CTA, book your ride for next week already today. So this might lead to additional significant load on the ride booking service. What we can do now is to decouple even parts of this service and connect them with messaging. We now have only the pre-booking submission resource here at the first stage, and it takes the incoming payload and forwards it into the pre-booking notification topic. And then it can already answer to the client, we have accepted your request, we work on it. It will then go into a queue, and from there it can be consumed by the pre-booking processing resource. So we decouple now the reception from the pre-booking from the processing. Important for the customer is that we really can accept the pre-booking request. It's fine to have it really worked on a few seconds later. But with that, we can make sure that the ride booking service can really answer fast to an incoming request for a pre-booking. There's an additional campaign running now. Book now. Imagine it's prime time on TV. If you're still watching TV, I don't know, maybe you only stream. But let's imagine there's a nice movie on TV and the entire country watches that movie, and there's a commercial break, and you see the campaign, book your unicorn ride for next week already now. So from 1 second to the other, you might see millions of incoming requests. What can you do now? One approach, since you use your own mobile app, is to put an SQS queue even in front of your pre-booking submission resource. So the SQS queue will flatten the peak for your pre-booking submission resource, and then you can consume it afterwards. Again, it's crucial for the customer experience that we accept the request, but it's absolutely acceptable that we work on it a few seconds later. The next use case is instant ride RFQ. So since Wild Rides is a really progressive company, it has thought of a new use case. And here we can now make use of the scatter-gather pattern. So imagine you leave the hotel, you're outside on the strip, and you want to book a ride, or you want to call a unicorn to get you home to your hotel. But you don't want to get just any unicorn that is around. You want to book one that has the best offer for you, whatever best offer means for you. It might be the cheapest price, or it might also be that it has free drinks during the ride. Since this is Vegas, probably this is possible here. Okay, so the user uses the Wild Rides customer app, and it sends a submit instant ride RFQ request to the backend. The ride booking service takes care of it. Since an RFQ is something that is not done within a second or so, we also can immediately send a response to the client to accept it. Hey, we have accepted your request. We will now run the RFQ for you. And the ETA is X. And X is you would allow the customer to configure, okay, I want to wait maximum 5 minutes. So this is the timeout for my RFQ. It also gets back a link to a status resource that it can query afterwards about the current status of the RFQ. Now, the ride booking service forwards this request into the request for quotes topic. And all relevant unicorns in proximity would then get notified through the unicorn management resources, probably with a push notification on their mobile device. Hey, there's a potential customer around. Do you want to take part in the RFQ? So every unicorn can now individually work on their response, submit it into the RFQ response queue, and from there it is consumed by the ride booking service. While all this is running, the customer might want to get an update of the current status of the RFQ, so probably refresh the screen. The client would then send a retrieve RFQ status message request into the ride booking service, and while it is still running, as you can see, status running. Eventually the RFQ is done, then the result would look like this, and it comes with a link to retrieve the final result. So client sends a request to the retrieve RFQ result resource and gets back the final results, probably with an array of all the quotes. Now the customer can select the best quote from the result. Last use case I have today is fare collection. So in the first use case, we ended up with this architecture. Now we want to have a look into the customer accounting service, because we also want to make sure that we eventually charge the customer for a ride. And this is a perfect use case for Saga orchestration. Let's imagine we have 3 discrete steps that we want to follow here. And the first one is we want to do a credit card pre-auth. On the right-hand side, we can see a fraction of a state machine as it is visualized by AWS step functions. So first step would be the authorization. If this is successful, we get back a code from the pre-auth, and we can charge our credit card using the pre-auth code. If this is also successful, we would update the customer account and do all the homework that is required to keep our databases up to date and so on. By using a state machine and also having the branches for the sunny and for the rainy cases, we can treat all these 3 discrete steps as one distributed transaction. And we also can make sure that our systems remain in a consistent state. I'm slowly coming to an end, but I would also share a few resources with you. If you're interested in this topic, you can have a look at the AWS Compute blog. There are tons of blog posts there that also deal with messaging. If you follow this link, you will find all the blog posts that are tagged with messaging. We have been delivered also a hands-on workshop during this reInvent, actually 3 times. The last time was today at noon, so you cannot go there anymore. But this workshop is eventually also going to be a regular immersion day that AWS solutions architects can deliver. So, and the content of this workshop was basically that we implement the use cases that I have just shown. So you might want to speak with your AWS account SA on this. The chalk talk is also already gone, but maybe next time. If you keep one thing in mind from today, please, loose coupling is better than lousy coupling. As always, it would be great if you could provide some feedback. And other than that, I thank you for joining today. And that's it. Goodbye.